מעולה.
זה לא סגר את השיירינג, נכון? אפילו שאני לא ההוסט.
נכון.
זה
אני
רק
יכול להפוך אותך
להכתיב.
ל-co-host עכשיו. זה אולי מה שהייתי צריך לעשות. הנה. עכשיו אתה co-host, ואז שנינו יכולים לעשות כל מיני דברים. עכשיו אתה יכול. כן, רואים את המסך שלך מעולה.
רואים? מצוין.
אוקיי, אז יש לנו עוד 3 דקות. מכיוון שאנחנו מעט אנשים, אז מה שאפשר באמת לעשות זה לתת לכולם לדבר, אם אתם רוצים. הנה, אני עכשיו נותן לכולם לדבר.
שלום.
שלום.
שלום, שלום. נחמד לראות מיטאפ בישראל.
כן, תכף. אנחנו נראה כמה אנשים אנחנו, כי פעם שעברה אנחנו היינו יותר מ-20 איש, אז זה כבר היה קצת רועש. עכשיו זה אינטימי כזה, בינתיים יש לנו רק 10. אז ברוכים הבאים כולם, אנחנו עוד מעט נתחיל. בינתיים, אם מישהו רוצה להגיד משהו, להציג את עצמו, לספר, מוזמנים. טוב, אז בואו, אני מציע שבאמת נשאיר את השיחות נפש לאחר כך. עכשיו ניתן לאלון לספר את מה שיש לו לספר, ואלון, הבמה שלך.
יופי, אוקיי. Can you hear me okay?
Yes.
יופי. אז אני אציג באנגלית, כי בדברים טכניים האנגלית שלי יותר טובה. One second. Okay, good. So let's get started. So I want to talk about WebAssembly and the elusive universal binary, whatever that is. So the background here is the normal process of distributing binary executables. So you have your source code, compile it for Linux, for Mac, for Windows, and then you ship the appropriate build to the appropriate users. So again, this is just the normal thing that probably is what a lot of people have done. And so the source code might be 99% the same for Linux, Mac, and Windows, maybe just a little if-defing, but regardless, we still need to make a separate build. So we do have to have this kind of multiple builds situation. To make this a little more concrete, the use case that brought me to look into this area is a tool called Wasm-Opt, which is part of the Binarian project. As the name implies, it's an optimizer for WebAssembly, and it shrinks Wasm files by about 20% or so. So it's useful when you're shipping Wasm on a place like the web where code size matters. Okay, so we have builds for Linux, Mac, and Windows of Wasm-Opt for 64-bit Intel, and they're used in Emscript and in Webpack and other places, and generally speaking, everything works fine. But of course, nothing is perfect, so some users can't use them. They might be on ARM, they might be on 32-bit Intel, they might be on BSD or very new or very old Linux. And in general, build infrastructure just takes work. It's more work for every OS that you support. And sometimes a test or something only fails on one. So there is a lot of annoyance in this process that I'm sure is a familiar thing for people that ship binary executables. And so it's kind of natural to have a dream of a universal binary, a single executable that runs everywhere and at 100% speed. So this is just a simpler picture than before we take the source code, compile it once to a single build, and then we ship that single build to all the users, and somehow it works on all of them. So this is a dream, as I said. We can't get perfectly to this because there will be some trade-offs at least, but hopefully we can get pretty close. And one thing I want to stress now is this isn't necessarily a literal binary in the sense that it has to be binary executable code. The details don't matter. We want a universal build. We just want it to be fast and portable. However we actually implement it is sort of a detail. Okay, so we want it to be portable. There are two types of portability we need to care about. We need CPU portability, just the ability to do pure computation, to have a single build that runs on Intel, on ARM, that doesn't care about the CPU. And we need OS portability so that we can access APIs like printing and files and maybe graphics and audio. And we need a single build to do that on any OS. So it's worth mentioning the web in this context because it has one of the best portability stories. It's very rare to find CPU or OS specific bugs actually. So there are bugs on the web, but they're generally browser specific bugs, which is a completely separate issue. And the way the web does this is to just disallow anything non-portable. You're not allowed to access the underlying CPU directly. You're not allowed to access the underlying OS. That used to be possible through plugins like ActiveX, but those are mostly a thing of the past at this point. Off the web, we have things like Java, .NET, Python, Node.js, and other virtual machines. And these VMs provide full CPU portability in one way or another. So in Java and .NET, they have a bytecode format. And in Python and Node, they run script languages. So it's just source code anyway. On the OS side, the story is somewhat different than the web. So they do typically allow some OS-specific operation. So it's not as portable as the web, but it does give you more power, which maybe you want if you're running your own code on your own server. So maybe all your servers are Linux and you want to use a Linux syscall or something else that's just more powerful. So there is a trade-off here. Okay, so bringing this a little back to the topic. So if we have a language that compiles to executable code like C, C++, Rust, or Go, can we use a VM? We kind of want to use a VM because that'll give us a portability story. So obviously the whole context of this talk is that these compile to WebAssembly. And WebAssembly, just like it does on the web, solves CPU portability. That's really what it's for. So we need a concrete VM that supports WebAssembly off the web. And there are two main families of options in this space. Okay, there's Node.js and Dino. These are VMs built on the V8 JavaScript engine. which supports both JavaScript and WebAssembly, so you can run Wasm on these two VMs. And there are Wasm VMs, which is a new family of runtimes that only do WebAssembly and nothing else. And these are things like Wasm Time, Wasmer, Watham, Wasm3, and a bunch of others. Okay, so what APIs can we use on these VMs? So starting with Node, Node provides Node.js APIs, and there's just a useful set of OS operations on files, reading and writing, processes, etc. There's an example on the slide of some JavaScript that does read file sync, that is, it reads data from a file. So as you can see, there's no special sandboxy model, kind of like Python and others. You just get direct access to files on the system. And reading data from a file is going to be very portable, but there are, as I said, other operations that might not be, that you could notice OS differences. And also this is JavaScript, so like the comment says on the bottom, Wasm can't directly call read file sync, but just like on the web, it can access them indirectly. So anything the Node.js APIs allow us to do, Wasm can call some JavaScript that'll call those APIs and do it indirectly. On Wasm runtimes, on the other hand, we have the WASI APIs. WASI is the WebAssembly system interface, which is meant for non-web environments. It's important to stress that WASI is not just a bunch of familiar APIs brought to Wasm. It could have been just read file, write file, etc., just straightforwardly. But it's actually not. It's a new approach to writing an OS interface layer in a new way. It's kind of a replacement for something like POSIX if we were thinking about it from scratch and trying to do it right, sort of. In particular, some differences are that WASI uses capability-based security, which I don't have time to get into, but kind of very briefly, on the last slide, we saw how we can read directly from a file. In WASI, that code needs to first be given the capability to read from that specific file. So it needs to be given the capability ahead of time, and that means the entire OS interface needs to be designed for this. But it does give you a lot more fine-grained control over security. So it's a very useful property. And WASI is still fairly new, but it seems to be targeting a stricter portability than things like Node and Python. So it's maybe closer to the web, but we'll see. So there's a lot more to say in this space, but maybe to summarize the big picture in our context, WASI is supported on Node.js too, so it's not just for Wasm VMs. It'll have very broad support, I believe. In the long term, it'll probably be the best option for many things, but it is still early though. As I said, it's new, and it's designing a new OS interface in a new way, so that will take time. And also the more strict security and portability will limit what can be done. So it's the trade-off I mentioned earlier. There might be cases that you're running your own code on your own server where WASI doesn't let you access a Linux syscall that would have been very useful for you. So WASI might not work for everything in the long term, but for the things that it does work, which hopefully is almost everything, it'll probably be the best standard option. Okay, so that was background generally for this space, but let's get back to the concrete example. So we have the Wasm tool, and we want to compile that to some kind of a universal build, just one build, and we want to ship the universal build to different OSs, different CPUs, etc. So what can we actually do here? So can we compile to Wasm VMs? So Wasm needs only basic file operations, read from a file, write to a file, which WASI has all the support we need. But Wasm needs either C++ exceptions or setjump. It has an internal interpreter that helps us and needs one of those features. WASI does not support that yet. So Wasm itself will get exception handling in a proposal that's being worked on now, and WASI will support setjump and exceptions using that, but that's not here at the moment. So we can't compile to Wasm VMs right now. What about compiling to Wasm on Node.js? So in Emscripten, we support setjump and C++ exceptions when building to Wasm plus JS. So we need a little bit of JavaScript to help us. So there's a call stack here. So the call stack goes up. So you start from main, a Wasm function calls foo, a Wasm function. And the key idea is we call out to JavaScript to do things like a try, catch, or a throw, because JavaScript has try, catch, and throw. And then if a throw happens, it sort of unwinds back to the last try, catch. So it's kind of an interleaved stack with Wasm and JavaScript. And that lets us basically leverage JavaScript to do the exception stuff for us. And this works anywhere that we have both Wasm and JS, which includes the web and Node. And it's also very easy to compile Wasm opt with emcc. So you just run emcmake before the regular cmake. Emcmake just tells cmake to use emcc instead of the system compiler and so forth. And then you run make, and that's it. Very, very easy. The defaults are mostly okay for that. The one default we do want to change in this context is Emscripten's normal output is fully sandboxed. But in this case, we want direct local file access. We want to read from a file on the local system and write to it. So we have an option node rawfs, which gives you raw direct access to the file system. And it's very easy to use. You just tell cmake, here's another linker flag, -s node rawfs. And that's it. And then we get a build and we can run it. And it runs almost like a normal executable. So we need to type node before the build because it runs in Node. But aside from that, we type node and then wasm-opt.js, and then we give it the input file and other command line parameters like the optimization level -o, and we tell the output file. And then we get the expected output. That is, it did the work that we wanted it to do. In this case, you can see the input file shrank by about 20%. So we have a build. And the great news is this has full CPU and OS portability. So it's a universal build, just like we wanted. So on the CPU side, it's just WebAssembly and a little JavaScript. And just like on the web, those are fully portable. And on the OS side, we just read and write from files. So the Node.js APIs are fully portable there too. So great so far. What's not that great is we are 28% slower. So this is a portable build. We expect some overhead due to the portability and the sandboxing of Wasm. Maybe 28% slower is not that bad. It's not great. I mean, for Wasm-opt specifically, I probably wouldn't want to replace our standard builds with it, but maybe this could be an optional build on the side. What is, though, definitely not great is every time we run node Wasm-opt, we compile the Wasm. And that takes about a second every time. So even just typing wasm-opt --help, which should be instantaneous, takes that second. And if you have a test suite with a lot of small files or something else, it's very noticeable and very annoying. So it's not a good user experience. There is a solution for this. So you can cache the compiled Wasm code, which works on the web. So after you visit a website once, it'll cache it. The second time, it'll just load the compiled code instantaneously. Node.js doesn't do this quite yet. Actually, Node.js had an API you could build code caching on top of, and in scripting, we added that. But some underlying change prevents it in Node 14. So right now, we can't sort of speed up the loading in this way, but hopefully in later versions of Node, this will become possible eventually. Okay, so the story so far is kind of negative, just bad news. We can't do WASI because it doesn't have set jump. We can't do Node.js because startup is slower. So that's maybe not a deal breaker. Maybe we could ship the build, but it's such an annoying user experience that I don't know. So maybe we should just wait until things improve, because as I said, these are limitations right now. WASI will eventually get set jump support, so we can run in Wasm VMs. And Node.js will probably improve the startup thing by adding automatic caching or some other mechanism. So we could wait, but I have about a third of the talk left, and there is another option. So I want to talk about a tool called Wasm-to-C. As the name implies, Wasm-to-C compiles Wasm-to-C, and it's part of the WebIt, the WebAssembly binary toolkit project. It was written by Ben Smith. So what can you do with it? The full workflow is something like you take your source code, compile it to Wasm using your Wasm toolchain, and then you compile the Wasm-to-C using Wasm-to-C. And then you have C code, so you can just compile it to an executable using Clang or GCC. And this is very easy to do. So just like before, we can just do em-cmake. CMake, we just need to tell Emscripten to use Wasm-to-C. It has integration, so we just need to add a -s Wasm-to-C linker flag. And that's it. Then we do make, and then we get this wasm opt.wasm.c file, which you can see on the line with Clang. And we just compile it like a normal C file, and then it runs just like a normal executable. It just wasm opt, give it the input parameters and other command line arguments, and we get the same output as before. So it works. It's kind of an odd way to compile, but it works. So before I talk any more about this, this is kind of a little silly, right? We started with C++, we compiled to Wasm, then we compiled to C. So we're kind of back with something we need to compile. What have we actually gained in this whole process? So I think we have gained something very useful. We've simplified what happens on the user's machine to the simplest possible compilation. What I mean by that is, so on the developer machine, we compile source to Wasm using our Wasm toolchain. Then we compile Wasm to C. We ship that C code to the user machine. On the user machine, we need to compile the C to an executable. And I say that's the simplest possible compilation because there's a C compiler everywhere. That is, we don't need a new compiler for if the source code was in C++ 20 or Rust Nightly or something else. We don't need any new thing like that. Just a plain old C compiler is fine. So it's a very low bar that's pretty easy to have. And we might have had a complex build system on the developer machine. When we compiled source to Wasm, maybe it compiled lots of files, maybe it downloaded things from the internet, maybe it built some things and then ran them as part of the build process. It could do any sort of things. But the end of that whole process is a single C file that we ship. So on the user machine, it's just one call to Clang or GCC to compile that C file without a build system even. So we do still need to compile on the user machine, but it is the simplest possible compilation, I think. And this fixes the issues we had before. So startup is instantaneous. We end up with a normal executable, really. So we do need to compile it on the user machine once, but after that, it just starts up every single time with 0 delay. It's also pretty fast to run. Throughput is only 13% slower. So it's about half the overhead the Wasm had. And it's probably a bit better because Clang and GCC are really, really good at compiling and optimizing C code. So here are a bunch more benchmarks, which might be interesting because that 13% thing was on Wasm opt, which is one program, but maybe that was just we got lucky. But no, the overall average overhead is about 14%, so it is pretty low overhead. So this is the Emscripten benchmark suite, which has about 20 benchmarks. About half of them are interesting real-world code, like the CoreMark benchmark, the LinPack benchmark, Box2D and Bullet physics engines. So on a wide variety of real-world code, it does have fairly low overhead for a build that's sandboxed and portable. And there's actually a surprising speed benefit. So there were 20 benchmarks, so it might have been hard to notice on the last slide, but Wasm-to-C actually beat the regular native build on 2 of those benchmarks. So that seems kind of odd, maybe. How can we actually beat just regularly compiling the program instead of compiling it to Wasm, then to C, then to an executable? So it's beating all 3 of the regular compilers on these 2 benchmarks. And Lua binary trees is real-world code. So what's going on is Wasm is a 32-bit architecture. So on a 64-bit host, like where I tested, like practically all of our laptops probably, it's kind of like the x32 ABI. So the x32 ABI on Linux is an ABI that says we're on 64-bit Intel, so use all the new registers, use all the new useful things that it brings, but don't use 64-bit pointers. Use just 4 bytes instead of 8 bytes for pointers, and that saves memory. So you're limited to 4 gigabytes of memory in that case, but if you're okay with that limit, the memory savings can be useful. And in fact, that explains what's happening. So on Lua binary trees, we actually use about 30% less memory to run, so better cache usage and so forth. So it turns out Wasm is kind of an easy way to get benefits like X32, which can help a lot in some cases. Okay, so I might describe Wasm-to-C as sort of VM-less Wasm, Wasm without a VM. But it's still Wasm in the sense that it's 100% as portable as Wasm in a VM would be. So it's easy to write C code that's not portable. You just use the long type or some other type that will change depending on the compiler and the system. But in this case, we emit portable C code that should compile the same everywhere. So we could have bugs, but in principle, it's possible to write portable C code. It's also 100% as sandboxed as Wasm in a VM would be. So it'll trap on out of bounds, it'll trap if the stack overflows. It does all the same safety checks and guarantees that a VM would. It just does it without a VM. So it actually doesn't have to be this way. For comparison, Wasm-to-JS, which compiles Wasm to JavaScript, actually doesn't have these two guarantees. And if you get a link to the slides later, which I'll send out, there's a link here to a discussion about whether maybe we should do something similar in Wasm-to-C or not. There's some interesting discussion there, I think. Okay, what's the API story here? So Wasm-to-C itself is agnostic to APIs. Wasm-to-C translates Wasm to C. A Wasm import becomes a call to a C function. So it's something kind of external to the Wasm, so Wasm-to-C doesn't do anything with it. It just sort of lets you provide it. And that means that Wasm-to-C can be used with any Wasm toolchain if you make a C runtime that implements the imports and has all the support that the Wasm needs. So in Emscripten, I've been working on a runtime for Wasm-to-C that basically implements all the APIs that we need for Wasm executables from the Emscripten toolchain. So we use WASI APIs as much as possible, and therefore the runtime supports a bunch of WASI. We also do things like add secsjump support and other things, and that's how we could run Wasm opt actually. And all those benchmarks, which as I said, were a bunch of real world code. So quite a lot works right now. Okay, what's the current status of Wasm-to-C? So it is fairly new. There might certainly be bugs. The C code builds on Clang and GCC on all platforms that I've tested. But again, there probably are bugs. And in particular, we know we need help with things like the Microsoft Visual Studio compiler, because right now the C code uses built-in CTLZ, which apparently is just something on Clang and GCC. So we need to add some if-defing for different compilers. So it's not as portable as it should be yet. We made a single C file. If you use this, you'll probably notice that on a big project, these single C files don't compile fast, especially with -02. And this makes sense. C compilers are not intended to compile single huge files. So we should probably add an option to separate the output. We just haven't done that yet. And as I said, the Wasm-to-C runtime in Emscripten supports pretty much everything, but it is still missing a few things that we just haven't gotten around to, like C++ exceptions don't work yet. Okay, so all of this is open source. By all of this, I mean all the compilers I mentioned, all the VMs. This is all open source. And if this is a field that interests you and if you'd like to make it better, then the people working on these projects, I'm sure, would be happy to get help. Okay, so just a few more slides to sum up. So the idea here is you take your source code, compile it to WebAssembly, compile that to a universal C build. And then that one build you can ship to different OSs, different CPUs, all your users, no matter what machines they have. And that universal C build actually works surprisingly well for a few reasons. So it's easy to do on the developer machine. We saw how easy it is to do. It's literally just a few lines to basically use an existing Wasm toolchain and to use Wasm-to-C. So for the developer, it's very easy. It's easy to build on the user machine, so we still need to build that C code, that's true. But it is sort of the simplest possible compilation. As I said before, it's just one C file, no build system, and it's just plain old C. You don't need a new compiler. And of course, the big point here is it's a single build for all CPUs and OSs. So we just build once and then ship that everywhere. And this is a pretty nice property. So we don't need a builder for Linux, a builder for Windows, a builder for Mac, and so forth. In fact, we could just make the build on the developer machine because it doesn't matter where you build it. It'll be the same everywhere. Build once and then ship anywhere pretty much. And this is pretty fast. So you need to compile it the first time. But after that compilation, you get a build that's just a normal executable. So it's super fast to start up. And it's pretty good in throughput too. It has about 13, 14% overhead. So there is some overhead, but it's pretty low for a sandboxed portable build. Okay, I do want to stress that in the long term, I think Node.js, Wasm VMs, and WASI will fix the issues we saw. So we couldn't use them today because of the limitations we ran into. But after they fix those, probably VMs will generally be the best option in this space. That is, you'll compile to Wasm and use Wasm as your single build. And then you'll ship that to a user, and the user will need to have a Wasm VM to run it on, or Node.js or some other VM, but that'll be the straightforward thing to do. But with that said, there is something, the more I work on this stuff, there is something really nice about VMless approach. Just not having a VM at all, not needing one, is simpler for some things, like what I talked about here. And there are a few more use cases too, but I do not have time for them here. That's it. That's all I have. Thanks for listening. Happy to take questions.
Thank you.
Thanks, Alon. Thank you very much. That was very, very, very interesting from my point of view. There are already a couple of questions in the chat. I see Michael asks something about comparing to .NET and JVM.
I can ask this question if you like.
Okay.
Yeah.
Sure.
Well, I could repeat the question. So the question is, how does this portable IR compare to .NET IR, JVM IR? So basically, so WebAssembly is a portable IR that is similar to them in the sense that it's portable. It does have a bunch of differences that might matter more or less. For example, .NET IL and Java are kind of focused on this object-oriented model that works well for Java and C#. WebAssembly focuses more on the family of languages that compile to executable code, like C and Rust and Go, as I said. We actually can't compile Java to WebAssembly yet. So it's kind of currently useful for different languages. We do intend, though, to add GC to Wasm, and at that point, maybe it will become very similar in what it can do to the JVM and the CLR.
Maybe I can clarify the question.
Oh, sure.
So I assume that Wasm, by definition, should be language agnostic. Therefore,
eventually, yes.
Yes, and therefore, language shouldn't matter at all. If I understand correctly, the blocking factor with languages that you just mentioned is presence of GC.
Exactly, yes.
So if I put GC aside, because it could be implemented as a library, what actual benefits we have in the compilation toolchain that you described?
Well, so I'm not sure what you mean by implement Wasm as a library. Implement GC as a library. There's maybe a lot to talk about there. But the current benefit of this is you can take a C++ or a Rust or a Go program and compile it to WebAssembly, and it'll run at almost full speed. You can't do that with a JVM or CLR. You can't compile a C++ or Rust or Go program to them. and have it be as efficient as WebAssembly can.
I kind of challenge this. Being .NET, I'm from the .NET world, and I can clearly generate ahead of the time compiled, fully native code with garbage collection. So I guess other than GC, if you look from different perspective on the compilation toolchain that you described, second most strongest point that you had, but it's really easy from development point of view, correct?
Yeah, yeah.
And I would like to challenge this, because let's understand how many mental models a developer needs to have to develop using this tool chain. First, I need to understand the language that I'm using to write the code, which is, let's say, Rust, with syntax and semantics and memory model that I have in my mind, or C++, okay? After this, I have compilation into a different runtime, which is Wasm runtime. After that, I have completely different semantics of C runtime with its own quirky behaviors and undefined behaviors. At the end, I need to define all that. Isn't it creating exponential explosion of platforms that I need to maintain? Pretty much I'm doing standard cross compilation with all the implications of cross testing.
Well, I mean, there is some risk for this, that's fair, but think about what happens with WebAssembly on the web. You compile a C++ or Rust program to WebAssembly and you run it in Firefox or in Chrome on different CPUs, different OSs, and it just works. I mean, so WebAssembly does have a semantics, but it'll be the same wherever you run that WebAssembly. So once you get to WebAssembly, nothing should change after that. So even that we compile the WebAssembly to C, we preserve the semantics when doing it. As I said, it's still 100% is portable and 100% is sandboxed. So if you find any change in behavior between the WASM running in a VM or the WASM running after being compiled to C, that would be a bug that we need to fix. So we have tested this and fuzzed it, and we're not aware of current bugs, but there certainly could be. But in principle, once we fix the bugs, it should not have any issues with the C part.
I truly believe that it's achievable in abstract computation model, where you don't have dependencies on WASI interface. The moment that you introduce WASI interface, you open the can for undefined behaviors. Look at the file attributes and file close semantics, file append semantics, multiple streams in the same file, ZFS versus NTFS, snapshots on NTFS, all that, or ZFS by itself, the monster. How, the moment you expose WASI, your portability is gone.
So I mean, I wouldn't go that far, but I think you make a valid point that it is very, very hard to make something like WASI or any OS abstraction layer portable. So this isn't a problem for WASM. WASM itself should be 100% portable, period. WASI certainly will have challenges, and that is one of the challenging parts in the WASI standardization process that's happening right now in figuring out how to make an OS layer that's really, really portable. Again, even more portable than what Node.js and Python, the JVM allow today. So everything that you said is very true and will be hard, but hopefully the WASI process will be able to do it. I do want to add, though, that in the concrete case that we have here, all we do is load and save a file. So for simple applications, this will be fully portable even today. But you're right that there are corner cases that will be very hard to iron out.
Yeah.
So yeah, but that's a very good question. It's very difficult to achieve full portability at that layer. It's never been done really, not perfectly.
Have you worked with or have you checked the work that Kevin Hoffman is doing on actors and runtime, WASI runtime with a rich system interface. When I'm compiling Rust actors to Wasm, and I plug in system capabilities beyond defined in Wasm.
So I'm not closely, so I haven't followed that very closely, but I have seen a talk and read some docs. So I'm aware in general of the idea, but not the details.
Michael, can you share maybe some links to the chat or to the meetup group?
Yeah, I will do.
Okay, because I haven't heard about it too. Okay. Folks, any more questions? Thoughts? Okay, I've allowed everyone to talk, so everyone can talk. Okay, here I see something in chat.
Oh, yeah, so there's a question. I'd like to hear about support for graphical interfaces like OpenGL. Yeah, that's a good question. So there is some work in WASI to standardize something like WebGPU. WebGPU is a new spec for portable, fast graphics in the browser. And apparently it's a fairly good fit for WASI because it supports the capability model. I haven't followed this closely, so I don't know what the current status is, but hopefully eventually this will be an option. And we also have the capability to add, that is, if you use the Wasm-to-C approach, you could just add to the C runtime some OpenGL import implementation. So you could do that by yourself, but then you would have portability and other questions that you'd need to think about very carefully. I've not thought about that at all.
אוקיי.
Hope that answers the question.
אורן שואל אם אפשר לשאול משהו שלא קשור להרצאה ספציפית, אז אני מציע שקודם נראה שלא נשארו לנו שאלות בקשר להרצאה של אלון, ואז אפשר לקשקש על נושאים שלא קשורים להרצאה ספציפית.
כן, זה נשמע טוב. So a question, what's your take on Blazor? In general, in general, I think Blazor is really interesting in that it lets you write .NET and run that on the client side on the web. I think it's a great, it shows what you can do with that tech. I recently saw a demo where they actually show full stack debugging of a Blazor application. So it's really very impressive. But was there something in particular that was in the context of this talk? Maybe I'm not seeing it.
The reason why I'm bringing up Blazor, because it's very challenged and many people have opinion on how it should be or how it shouldn't be done. Specifically, we are talking about execution of computation kernels in fully sandboxed fashion in browser. I think it opens a lot of opportunities, even in browser, beyond UI rendering. And this direction I see as very promising. And you're currently working on something completely orthogonal. You're working on Wasm-to-C. And when you made the choice and you prioritize this direction, you saw more potential. I guess you saw more potential in Wasm-to-C than in direction that Blazor takes. So I wanted to hear your opinion. Why do you think Wasm-to-C is more prominent, is higher priority than put all the effort in creating, in focusing on web effort, in the front-end development using, what's driving your priorities?
Yeah, that's a fair question. So I wouldn't say that there's an assumption that these things are competing in some sense and I'm picking between them. So I don't think I want to or need to pick, but in terms of the priorities, so Wasm-to-C is something that I think is interesting, and I've worked on it for a bunch of reasons because it has a bunch of use cases that I think could be very useful, including the one I talked about here. but I definitely do not think that it is the most important thing in the Wasm ecosystem at the moment. 95% or so of the work that I do is fully focused on the web side, because that is the ecosystem that I've always been and still am most focused on. I don't think Wasm-to-C helps that ecosystem directly, which is why I don't spend a lot of time on it. But I do think it helps a bunch of use cases that justify spending at least some time on it, and I'm curious to see what other people will find to do with it. So that's why I've put some time on it. But again, I fully agree that the web ecosystem for Wasm, including things like Blazor and many other things, is a thing that I care most about. Does that make sense?
Yeah, absolutely. Thank you.
Cool.
Okay. Any more questions to Alon? Well, I guess not. Okay. So has anyone tried running the results of Wasm-to-C through Emscripten?
Yeah, to see how the code mutates. Yeah, so compile C to Wasm, Wasm to C, C to Wasm, and then run that. So we have actually done this. I actually do this as part of the fuzzing effort that we do on Emscripten in the Binarian project. So we generate we have good support for generating random Wasm files. That is not just random binary and then checking if it's actually a valid Wasm binary, which 99% of random binary data won't be. But we can generate valid random Wasm files easily. And we do fuzzing with that. And as a way to test Emscripten, we actually compile those Wasm files to C and then run that on that. We can also fuzz GCC and Clang that way. So yes, we actually have done this and it works pretty well. I didn't measure performance carefully, but I didn't see that there's any significant overhead. That is, I mean, for the same reason that when you compile Wasm-to-C output with Clang, it's almost at full speed, just at 14% overhead. It's the same with EMCC. That is, you compile it again to Wasm, but again, it gets almost back to the original speed. So it does work well. The use case for that, again, all I can see is fuzzing at the moment, but it's at least fun to do.
Exactly. Okay. טוב. הנה השאלה של אורן.
Oh, so there's a general question about bugs. We found bugs related to graphics on Emscripten in the browser. Should we report them on the Emscripten repo or the browser? We couldn't make a separate bug reproduction in some of the browsers. That's a good question in general. It's not always easy to know what to do. If you're not sure, it's always fine to open a bug in the Emscripten repo, and then we'll help you figure out where to put it. But more specifically, if you can generate a test case, then I would just see if the test case works on multiple browsers. And if you can confirm that it just happens in one, then it's most likely a bug to file for that specific browser. But again, if you're not sure, please feel free to open bugs and we'll help out.
Alon, I have one more question.
Sure.
I think that modularity and it's really critical part of the progress of this project. And C and C++ have a lot of issues in this area. Specifically, even basic concept of DLL is not defined in the standard in C++. And the linking is not something defined in the standard way. An exception between C++ models, it's something that does not exist. It exists only within single DLL. And it's really a function of what environment you use and what compiler do you use. So how this is going to work in Wasm in general? What's the approach going to be? how multiple modules going to communicate exceptions in between the modules, and what's the format, what's the expectation?
That's a good question. I don't know the full answer, but I can say that we are working very carefully on both the exceptions proposal for Wasm and the dynamic linking proposals. There's a new module linking proposal in particular for Wasm. So we are thinking carefully about each of these features separately. And in general, in the Wasm ecosystem, there's also a movement to think about how Wasm modules compose, whether they're linked at runtime or at compile time, which hopefully that shouldn't matter. So I don't know the answer to the question, but I hope that as we're working on these pieces, we will actually have a concrete answer that works in a good way for it. But it is pretty early. Again, we don't have either a shipped exception spec or a shipped linking spec. So it's hard to see that far ahead, but certainly we do want to get there, and we do want to eventually specify it properly, because we don't tolerate sort of undefined behavior or other weird things like that. So if we do it, it will be spec'd out.
Thank you.
Does that answer the question?
I got the answer.
Cool.
Okay. Well, looks like there are no more questions, אז אני אעבור לעברית. אלון, תודה רבה.
לא דבר, היה כיף.
כן, כולנו מודים לך, גם אחלה הרצאה, אחלה תשובות, וכמובן כל העבודה שלך מאוד מאוד חשובה.
תודה.
זהו, טוב, תודה רבה חברים. אני רק אזכיר זה היה המיטאפ השני שלנו, ואנחנו כמובן רוצים שיהיה גם השלישי, גם רביעי, אז אני אשמח שמי שפה עובד עם WebAssembly, ואפילו דברים קטנים, נגיד אורן, נתקלת בבאג, אם תצליחו לפתור את הבאג, אולי תספר לנו איך פתרתם את הבאגים. קיצור, כל דבר, דברו איתי ואנחנו נשמח לארח אתכם. אני חושב שנבנית לנו פה קהילה מאוד חמה ונעימה.
תודה רבה.
טוב. תודה רבה. יאללה, ביי לכולם.
ביי.